Hello everyone, I am Saptarshi Hajara from Research Institute of Sweden, and today I'm going to be discussing our Backscatter platform designed in context of the HumanScatter Digital Futures project. So I will start off with the need for Backscatter platform. So in traditional RF transmitters, the transmitter generates its own carrier locally using some kind of local oscillator mechanism, and then this carrier is then mixed with the incoming data stream, and the data modulates the carrier, and we have finally the modulated signal which is sent over the air. And however, the local carrier generation as well as mixing are very expensive operations, so which means that to have both these operations on the device, we will need a higher amount of energy for doing packet transmissions, and it makes it hard to squeeze the energy requirement of these devices such that we can design devices using local carrier generation and mixing without battery reliably. So this is where backscatter communication comes in, and backscatter communication basically acts as a RF switch where the external device, probably a device with higher energy resources, generates a carrier wave, and the backscatter tag switches between two states, reflection and absorption, and the data controls how the tag is switching between the two states. And based on how, so this is how the data is modulating the carrier, because like data is saying when the carrier wave should be reflected or absorbed, and we get the modulated carrier wave with the data as the backscatter signal, which shows where the zeros in the data should be and where the ones in the data should be. And for the context of the HumanScatter project, we have developed a backscatter tag using an FPGA platform. So we encode our light sensor data as our data payload for 15.4 MAC layer, and then this data payload is sent to a 15.4 transmitter chain, which adds the header and the CRC to this data payload, and then the data complete 15.4 physical layer packet is modulated using PSK and FSK modulation. So for our tag, we do PSK and FSK modulation by switching through a set of inductive loads. So what it does is basically like when you have an impinging carrier, by switching between different sets of inductive load, we are changing the phase of the reflected carrier, which allows us to have a single sideband reflection. So what it means, like if we have a carrier at say frequency FC without a single sideband operation, we will have carriers at FC plus delta F as well as FC minus delta F. So we'll be blocking two spectrums when we just need one spectrum for sending our message through, but switching through a set of inductive loads allows us to concentrate all the energy into one of these FC plus delta F or FC minus delta F, and hence the backscatter signal is stronger, as well as it's at an offset from the carrier wave, hence the both carrier and the backscatter signal do not interfere with each other. And for the next steps, we are moving the backscatter tag platform to a memory mapped architecture, so which means that we will be easily able to modify and configure this tag platform by writing to register files, and this opens up possibilities of having multiple physical layers on the tag platform. And we are also moving to using more open source hardware tools, which allow us complete control over how the FPGA coding and programming is happening. With that, I bring an end to my presentation. Thanks for listening.